8.4 Bayes formula. And I know that one thing I'm going to be doing is calling this Bayes rule. So objectives. Student will be able to solve problems. Just be ready for that. Involving finding the probability of an earlier event conditioned on the occurrence of a later event using Bayes' formula, also known as Bayes' rule. It's not necessarily earlier and later. Here, by conditioned on, that's the key point. There's a dependence of one event on the other, so we call it earlier and later. But it doesn't necessarily have the time relation that they're talking about with earlier and later. Second objective is the student will be able to solve problems of the above type using a probability tree. So there's the formula and there's the tree. A survey of middle-aged men reveals that 28% of them are balding at the crown of the head. 28%. Moreover, it is known that such men have an 18% probability of suffering a heart attack in the next 10 years. 18% of those balding guys. Men who are not balding in this way have an 11% probability of a heart attack. Not balding. If a middle-aged man is randomly chosen, what is the probability that he is balding given that he suffered a heart attack? So this tree here describes the problem. You've got probability of, if you have a guy, he's middle-aged, probability that he's balding is 28%, and therefore that he's not balding, that probability is 72%. Of the balding guys, 18% of us are going to have heart attacks. That leaves 82% in the no heart attack group. But it breaks down a little bit differently for the not balding guys. For them, 11% will have a heart attack, 89% won't. Derivation of Bayes' formula. Here is a well-known rule of probability. Probability of B given H is the probability of B and H divided by the probability of H. Makes sense. Let's say we have the events B and H are represented by regions in a Venn diagram. So this region will represent, I call this a formula, and usually, we don't have balding and heart attack as the problem situation, and so often instead of the letter H we see the letter A in a box in a textbook as a formula that we're supposed to memorize. But H is the same as A, works the same way. They're just letters, they're just symbols. So here's event B represented by a region in this Venn diagram, and here is event H. And we're talking about the probability of B given H. Well, we're given that H is the case. So really, the only part of this Venn diagram that matters is this region here. This purple region, I mean, that's kind of like everything, because we are given that H has occurred. So the rest of this Venn diagram, it's really doesn't have anything to do with probability of B given H. Now if you think about it, since we're given H and we have to be in that purple circle, what's the probability in that case? What is the probability of B? What's the probability of balding among all those heart attack guys? Well, probability B in H, okay, the numerator, that happens of course in the middle where there's overlap. That's B and H right there. And if you think of the probability represented by the ratio of the black area to the total area of H, it makes sense that that would be represent the probability of B given H. A lot of times the formula is written this way, usually with a letter like A instead of H again, but if you multiply both sides of that equation by probability of H, then probability of B and H, probability B and H is probability of B given H, probability of B given H times the probability of H. Okay, times probability of H. And a lot of times that way is the way that we see the formula written. And we're going to use it both ways in this derivation. Okay, and by doing this derivation, we'll be able to wrap our minds around this formula, Bayes' formula, much better. Now if you look at the bottom, okay, if you look at the denominator, probability of H, you realize, especially when you think about balding and heart attack, that we're talking about a sum of two probabilities. Because if you're going to have a heart attack, then you're going to be balding or not balding. That's not profound. And so you can divide up the heart attack population among the balding and not balding guys. So this probability of heart attack down here in the bottom should be the sum of the probability of balding and heart attack and not balding and heart attack. Well, if you think about it, that probability of B and H can be rewritten as the probability of not balding and heart attack can be. So we're going to rewrite both of those probabilities. Okay, so big concentration right now. We're thinking about, how these formulas work together. But in the box here, what we have is a use of this version of the formula for probability of B given H. We've rewritten the left side, probability of B and H, as probability of B given H times the probability of H. except what we've done first is rewrite the probability of B and H as the probability H and B. Probability H and B.
Well,
that's the same thing, right?
We now
Balding
will
and heart attack
the
and balding.
numerator using the same
it's a
formula.
commutative operation.
The one which is
and so
equivalent
the purple
to
probability
this one
can
up
be
here in the
rewritten
corner.
as the blue probability.
The one that, well, if that's true,
you get when you
the
multiply
same
both sides by the probability
is
of
true
H.
over here,
And
with
have this
switched
probability.
again.
Probability of B and H, and
But now we have a different
H and B
way to write,
and so you don't have to follow all this.
The denominator,
but,
P
understand that
of H, the
you
probability of
should be
H.
able to reproduce it given
and
the
so
formula.
in that blue way
and
now
its
we're going
equivalent.
to let that be
But,
our denominator.
For now,
Okay,
just
so
to see where
we
the
will take
reasoning
that
comes from is
expression,
that huge
sufficient.
fraction.
But
there
now what we
into
have
the next slide and just
at
rewrite
this,
it.
what's the point of all this?
Well, the point of all this is now to write probability of B given H in terms of pieces that for the values of which we know. Okay? Because probability of balding, we know that. Probability of heart attack given balding, okay? We know that. And probability of not balding, we know that. And probability of heart attack given not balding, we know that. So we can substitute for all of these pieces numbers. Now, this is often the version of Bayes' rule that we prefer. And it's striking in one way, which is that a formula for probability of B given H becomes one that uses probability of H given B. So the sense of the conditional is flipped. The other thing is that in this version of Bayes' rule, you're going to get used to this, the top and the first product in the bottom are the same expression. So you see that repetition between the two. Well, as I said, we could substitute numbers. Probability of B we know is 0.28. Probability of heart attack given B is 0.18. Probability, and then that appears again, that same exact expression that we have in the top appears again down below. And probability of not balding is 0.72. Probability of heart attack given not balding is 0.11. And we get an answer. Probability of balding given heart attack is 0.389. Now we've been rigorous with the probability theory, but notice we even referred to the tree diagram in this derivation to make sense of it. So another method, way 2. Okay, same problem at the top, but now we're just going to work with the picture, and it's probably the best way. Another way to look at this problem is that we know that the person had a heart attack, so he has followed one of 2 red paths, which on my screen look like blue paths. Sample space has been reduced to these paths. So just as we kind of mentally blocked out part of the Venn diagram earlier, now we're mentally blocking out part of a tree diagram, concentrating just on the red or blue branches, not the black branches. So probability that he is balding is the 0.504. Okay. Given that he had a heart attack, we're only considering the heart attack, people. What's the probability of balding? Well, it's the probability of the upper path divided by the probability of the whole. Upper path has probability of 0.0504. Probability of the whole is, we're going to add all of this. Okay, that's the total. That is like the total number of possible outcomes. That becomes our denominator or field of probability. And so doing that division, we get the 0.389. So probability, given heart attack, probability of balding is actually pretty good. Notice that this is the same thing as that first step in the derivation, probability B and H plus, same thing, probability B and H plus probability not B and H. Summary of the tree method of solution. You do not need to memorize Bayes' formula. In practice, it is usually easier to draw a probability tree and use the following. In fact, you'd probably want to draw the probability tree even if you were going to use the formula. So the tree method statement of Bayes' rule. So you have U1, U2, UN, n mutually exclusive events representing different paths along the tree. Union is the sample space S. Let E be an arbitrary event in S, such that the probability of E is non-zero. Then this is true. Probability of U whatever, U1, given event E, is the quotient of the product of the branch probabilities leading to E through U1, the way we had it earlier. Okay, and for us that was just one branch, the upper one, divided by the sum of all branch products leading to E. Okay, so leading to heart attack, okay, we had two branches. And the sum of all branch products leading to E was the sum of the probabilities represented by those two branches. So make the tree, let the tree describe the entire problem situation with all of its conditional probability, and divide the probabilities represented in the successful branches by the probabilities, some of the probabilities represented by all branches.